Okay, greetings. I'm going to go over this mock version of your take home. And hopefully, me explaining this mock version will allow you to do your actual take home. Okay, so let's start with the beginning. What is the particle moving at constant speed? Okay, what is constant speed? Constant speed is when the speed is not changing, right? So this is it. This is velocity and time. So this is how velocity changes with time. So if velocity is now this is the value of velocity with respect to time. Uh, so just need to find the parts where velocity is not changing. And would that be here? No, because velocity is changing. Velocity is changing. Velocity is changing. Velocity is not changing. Velocity is changing. Velocity is changing. Velocity is not changing here because at t equals 5 seconds, the velocity is going to be 1, 2, 3. It's going to be 3 feet per second. At t equals 7 seconds, the velocity is going to be equal to 3 feet per second. So 3 feet per second, 3 feet per second. Nothing changes in between here. Versus compared to something like 2 to 4 seconds. At 2 seconds, the velocity is 0, and at 4 seconds, the velocity is 1. So there's clearly a change in velocity here, and that can be said for every other point except for this one. So let's go ahead and write t equal to, actually, you know what, I'm going to write it down. I'm just going to write 5 seconds to 7 seconds. Okay, when is the particle moving right? Okay, let's read here. Assume positive direction is to the right. This part right here is very important. Positive direction is to the right. So if the velocity is positive, this object is moving to the right. So if the velocity is, for example, 0, it's not moving anywhere. If the velocity is -1, that would be the velocity. And if the velocity was positive 5,438, and it would go like that, but to the right. So negative to the left, positive to the right, and 0 is neutral. Okay, so let's see. So in other words, when the velocity is positive, the object is moving to the right. So let's see. Okay, so if it's above this axis, it's positive because the velocity is going to be equal to a non-zero, a value that's greater than 0 when it's above here. So it's going to be everything that's above here. So from here all the way onto here at this point. Okay, so here's a question I want to ask you. I want you to think about it. Is the velocity, is the ball, is this a ball? This might be a ball. Okay, whatever this is. Okay, is the particle moving to the right at t equals 2 seconds? So right here, right here. Is the particle moving to the right or to the left at that point? 3, 2, the particle is moving nowhere. It's neither moving to the right nor the left. Remember, when the velocity is 0, it's not moving. So that means it's moving neither right or left. Okay, so when is a particle moving to the right? When this is positive, and it's positive from t equals 2 to t equals, let's call it 7.5, and no, 8.5. 2 seconds to 8.5 seconds. Okay. When is it moving to the left? Okay, so it is moving to the left. So if it's moving to the right, so if the velocity being positive means it's moving to the right, the velocity being negative means it's moving to the left. Okay, so let's find out when it's negative. Right here, here, and here. So everything under this right here. again, it does not include this point because at t equals 2 seconds, it's moving in neither direction. Okay, so when is it moving to the left? It's moving to the left from 0 to 2 seconds. And 8.5 to 11 seconds. I don't believe you have, I don't believe the original had two parts where it was negative. I believe it was positive and then it was negative like that. But for this version, you can see that there are two parts, so you'll need to separate them. It won't be from 0 to 8.5 because right here, it is positive between here and here. So it has to be separate from here and here. This needs to be, we need to put the two time ranges in which it is negative in this case. Okay, so next, when is the particle speeding up? Okay, so what is speeding up? That means when the velocity is, for example, 1, and then the velocity becomes 10. When your car is still, or maybe going 5 miles an hour, and then your car, because you're a responsible driver, it's going 400 miles an hour. These are examples of speeding up. The change in velocity is positive. Well, let me rephrase that, because you can also be speeding up, but in the negative direction. If you're in reverse, and you try to back out like a maniac, your initial velocity is -5 miles per hour, and then all of a sudden you're full sending it -6 miles an hour. I think you saw that one coming. Okay, so this right here, you are speeding up but in the negative direction. So change in velocity is negative at this point. But if the speed, let's take the speed. Okay, if the acceleration and the velocity have the same sign, this is speeding up. If they're both positive, they're both speeding up. Because if you think about it, if you're accelerating, if you're going backwards and your acceleration is negative, you're going to be moving faster but backwards. If your velocity is positive and your acceleration is positive, you're going to be moving faster but positive. You're moving positive. Your speed was positive, and then your change in speed is positive. So you're going to increase positively and become even faster over time. Okay. So when is the particle speeding up? When the velocity is, when the acceleration and velocity are in the same direction. So in other words, when it's increasing. So if you don't know, I'm going to tell you right now, this is 1, this is 1, this is not 1 right here. This one is not, this is not, this is not, and this is not. This is right here, and this is not. Okay, so let's visualize. I'm going to go ahead and explain why. Let's visualize what's going on here. Right here at this point, your velocity is -2 feet per second. So let's imagine that you're going this way, -2 feet per second, and then all of a sudden your velocity becomes 0 feet per second. Over 2 seconds, it becomes 0 feet per second. It goes from -2 to 0. Imagine you're walking backwards. If you're walking backwards, right? You're walking backwards at -2 feet per second, and all of a sudden you stop moving. You can see how you have slowed down. You have gone from moving to not moving. You have gone from a higher speed to no speed at all. Okay, so now why is this part right here? Why is that qualify as speeding up? All right, so let's imagine it again. You say you're standing still right here, which is right here at 2 seconds. You are standing still, and at 4 seconds, you have a velocity of 1 feet per second. You have a velocity of 1 feet per second. So you can see how you've gone from standing still to moving. You have sped up, and from here even more so. You've gone from at t equals 4 seconds. You've gone from 1 feet per second. You've gone from 1 feet per second to what is this? 3 feet per second. At t equals, this is not 1 second. This is 2 seconds. At t equals, I'm tripping again. This is not 0 seconds. My apologies. Okay. This is t equals 2 seconds. T equals 4 seconds. And t equals 4, 5. T equals 5 seconds. So this is what's going on here. Okay, so you've gone from moving at 1 feet per second to 3 feet per second. You've gone from moving like this to this. You can see how you've gone from moving slow to moving faster. Hopefully you can see my cursor, and that made a lot of sense. If you didn't, I think you should be able to try walking 1 feet per second, and then all of a sudden 3 feet per second. You'll see you have sped up. So what about this one? Okay, so you are standing still right here. You are standing still right at this point at t equals 8.5 seconds. You're standing still, and then all of a sudden you start walking backwards. Negative 1 feet per second. You can see how you've gone from standing still to moving. You've gone from no velocity to some velocity, and you have sped up. You have sped up. The criteria for speeding up is not no velocity to some velocity, it is some velocity to even more velocity. So from some speed to even more speed. Velocity is just speed with a direction. If you take away the direction and the value has increased, for example, if you've gone from -3 to -5, if you take away the direction, right? This is 3 to 5. You can see that this is gotten bigger. If that happens, you have sped up. Okay. So when is a particle speeding up? From 2 to 5. 2 seconds to 5 seconds. And from 7.5 seconds to 8 seconds. Okay, so what is this slowing down? Let's see. What is slowing down? Slowing down, if remember we disregard the signs. If going from 3 to -5, we disregard the signs. If it is increasing, that is speeding up. So the opposite will be slowing down. 12 to 8. It's still 12 to 8 if we disregard the signs, and we can see that this is decreased for -100 to -99. It goes from 100 to 99. We can see that this is decreased and we're slowing down. So let's do it here. Let's do it here. When is it slowing down? When is it slowing down? Okay, so let's try. I know for sure that this is slowing down, but I will show you using this method I just showed you. Okay, so if the speed is 3, it goes from 3 to, let's take this point, 7.5, 8.5 seconds. So at 5 seconds, the velocity is 3 feet per second. At 7.5 seconds right here, and 8.5 seconds right here, it goes to 0. So we can see that this decreases. What about here? The slope is positive. Why isn't this qualified as uh, um, speeding up? Why is this slowing down? I'll show you. Let's take the values. At 0 seconds, the velocity is negative 2 feet per second. And then at 2 seconds, the velocity is 0 feet per second. If we disregard the signs, this goes from 2 to 0. And we can see that 0 is 2 digits less than 2. Well, not 2 digits, 2, whatever. It is less than 2. You can see that. So if we do that for everywhere here, 5 seconds. Okay, so 5 seconds to 7 seconds. 5 to 7, that's going to be the velocity of 5 seconds, 3 feet per second. The velocity of 7 seconds is equal to 3 feet per second. There is no change here, so it's neither speeding up nor slowing down. Okay, so what about the next part? Oh, we've already gone over the next part. We've already gone over here. Let's go over here. No, better yet, let's go over here. Counter example. 0 at t equals 2 seconds, we have 0. And at t equals 5 seconds, we have 3. Right there. Cool. So we've seen that the value increased. So if it's not decreasing, then it's not slowing down. If it's increasing, then it's speeding up. So that does not qualify. So what qualifies is here to here, here to here, here to here, and here to here. So let's write that down. When is it slowing down? From 0 seconds to 2 seconds, from 5, no, my apologies, this does not qualify, because there's no change in velocity, there's no change in speed here. So from 7 seconds to 8.5 seconds, and from 8 seconds, so 9 seconds to 11 seconds. So we're trying to figure out when the velocity is increasing. So that's when the change in velocity is positive. That's when the change of velocity is positive. Okay, so let's calculate. We'll have to do actual calculations here to find it. None of the methods I show you, the speeding up, slowing down, that method won't work here because we're worried about increase in velocity, decrease in velocity, increasing being positive change in velocity, decreasing being negative change in velocity. So let's see. Okay, so how we would do it is we would calculate the difference between two different points. We would go this point minus this point, and I will show you why it's this point minus this point, not the other way around. Okay, so we're going to do it by first method, the correct method. Put a check mark here because it might be correct. 0 feet per second minus negative 2 feet per second. This is going to be equal to, well, negative, that becomes positive, so it's plus 2 feet per second. That's going to be 2 feet per second. And let's go for the other way around, which is going to be a big no-no. You don't want to do it this way, but I'll show you why. Negative 2 feet per second minus 0 feet per second is equal to negative 2 feet per second. And this is a big difference. This is a difference between going forwards and going backwards. This is a difference between walking. This is a difference between walking normally and moonwalking. There's quite a big difference here. So, let's see. Okay, so what this is saying is, from here to here, the velocity increased by 2 feet per second. Can we see that? You have gone from going in reverse 2 feet per second to going still. So your velocity, the change in velocity is going to be 2 feet per second. What about this one? This one suggests that it is negative 2 feet per second. What does that mean? So if you started here, right here, 2 feet per second, and the change in velocity is negative 2, that means it became even more negative. It went from negative 2 to negative 4, and that is not the case. That is not the case here. So the difference in velocity will be 2 feet per second, positive 2 feet per second, because you went from going in reverse to standing still. Your velocity was negative, and now it's not. Your velocity was negative 2, and now it's 0. You have increased your velocity by 2 in order to do that. So from here to here, we are increasing in velocity. So now you know it is this point minus this point. So in other words, future point minus past point. That's the way you want to be subtracting to find the difference. Velocity final minus velocity initial. Okay, give you the change in velocity. And change of velocity, if we're looking for speeding, for increasing, we're going to be looking for a positive change in velocity. All right, so let's see. From here to here, let's see. Okay, so we have 4 seconds. 4 seconds, the velocity is equal to 1 feet per second minus the velocity at 2 seconds, which is 0 feet per second, which is equal to 1 feet per second, which is equal to our change in velocity. So our change in velocity is positive 1, so this qualifies as our velocity increasing. What about here? What about this next point? From here to here. And I'm going after points that are straight, that there's no change in its direction, where the slope is constant. So at 5 seconds, the velocity is 3 feet per second. And at 4 seconds, the velocity is 1 feet per second. So the change in velocity is positive 2 feet per second. So right here, it qualifies. Okay, let's try this next point. This next point, the velocity is, okay, so from 7 to 5. I'm looking for points where the slope is constant. Okay, so from 7 to 5, at 7 seconds, the velocity is 3 feet per second. And at 5 seconds, the velocity is 3 feet per second. The change in velocity is 0 feet per second. Does this qualify or not? Well, in order for it to qualify as the velocity increasing, we would need the change in velocity to be positive. This is neither positive nor negative, so this does not qualify. Okay, what about this next part? From 7 to 8.5. At 8.5, the velocity is going to be velocity is going to be 0 feet per second minus the velocity at 7 seconds, which is going to be 3 feet per second, which is equal to a negative 3 feet per second. The change in velocity here is negative, so what does that mean? If the change in velocity here is negative, that means the velocity is decreasing. The velocity is decreasing at this point. So this would not qualify. The velocity is not increasing, it is doing the exact opposite here. Okay, so what about here? What about here? From 7.5 to 8. We got that this was speeding up before, but is the velocity increasing? Let's calculate. Change in velocity is going to be equal to the final point, which is going to be 1 feet per second, minus the initial point, which is 0 feet per second. My apologies. This is negative 1 feet per second. The sign matters here. So negative 1 feet per second. The change in velocity is negative 1 feet per second. So the change in velocity is negative. That means that the velocity is decreasing at this point. That means it does not qualify. It does not qualify as speeding up. As the velocity increasing. Okay, so let's look at that next point. From t equals, what is that, 9 seconds? From t equals 9 seconds to t equals 11 seconds. So at t equals 11 seconds, the change in velocity, the change of velocity from 9 to 11 is going to be 11 seconds, so 0 feet per second, minus the velocity at 9 seconds, which is negative 1 feet per second. Don't forget that sign. That sign will screw you over if you forget it. So negative plus negative and negative, that's positive. So that's plus 1 feet per second. That's positive 1 feet per second. Okay, so the change in velocity at this point is going to be positive 1 feet per second. So this does qualify. So we're going to go ahead and actually, let me change the color of this so it can be more descriptive. I'll make it blue, kind of neutral. I mean, yellow in this case would, I guess, be neutral. Let's make it yellow. At this point, it's yellow because there's no change. There's no change in velocity. So let's go ahead and write down everywhere it's green. So the velocity is increasing from 0 to 2 seconds. 0, 0, 1, 2, 3, 4, 5 seconds. 0 to 5 seconds. Not this, not this, not this. This. So 9 to 11 seconds. And 9 to 11 seconds. Okay, cool. So when is the velocity decreasing? All right, so the velocity is going to be decreasing everywhere it's red as we calculated. Whenever the change in velocity is negative. If you are not sure, I want you to calculate the difference in velocity from here to here. And remember, final minus initial will give you the change in velocity. And you need this to be negative. You need it to be negative for the velocity to decrease. Speed and velocity are different. Remember, speed is a scalar, which does not take a sign, and velocity is a vector, which does have a direction. In this case, negative and positive indicate its direction. Okay, so when is velocity decreasing? The velocity is decreasing everywhere it's red. So that's 7 to 9. 7 to 9. Are your answers to 6 and 7 the same as your answers to 4 and 5, respectively? Explain. Alright, so 6 and 7 should be the same as 4 and 5. This respectively means that 6 and 4 are the same, 7 and 5 are the same. So 6 and 4. 6 and 4, are they the same? No, they are not. They are quite different. It says 2 to 5 seconds, 7.5 to 8 seconds. It says 0 to 5, and it says 9 to 11. So they are not. They are different. Why are they different? Why do they care? Well, this is the particle speeding up? Is the velocity increasing? Some people think that this is the same thing, but you and I now know, at least hopefully. If you don't understand, go back to the video, see if you, go back a couple of minutes and listen to what I said, see if you can understand. But you and I should understand that velocity, increasing in velocity and speeding up are two different things. Okay, so speeding up. Remember, speeding up is change in speed. The change in speed needs to be positive for it to be speeding up, and negative otherwise. Neutral does not count. If the change in speed is zero, then it is constant. Um, yeah, if the change in speed is zero, it is constant. If the change in speed is negative, it is decreasing. If the change in speed is positive, then it's increasing. So speed does not take a sign. So let's go here. 5 seconds. Let's go from zero to actually let's go from zero to no. Okay, let's go from 0 to 2 seconds. Okay, so at 0 seconds, the speed, remember, is going to be velocity without a sign. The speed is going to be 2. Final minus initial. So the final is going to be 0, and the initial is going to be 2, which is -2. The change in speed at this point is -2. And does this make sense? Yes, it does. Imagine you're walking backwards negative 2 feet per second, and then all of a sudden you stop. And over time you stop. You have gone from moving with some speed to not moving. So your speed is 0 at that point. So your speed has decreased. Your speed, remember, it's just it's you can think of it as velocity without a direction, the magnitude of velocity. So this week. What about when velocity is increasing? That's just when the change in velocity is positive. So Vf minus Vi is positive. That's when it's speed. That's when it's increasing. So we've established that speed. We'll write down. No. Speed and velocity are not the same. Change in speed and change in velocity are not the same. Okay. How fast is the particle moving at time equals 4 seconds? Let's see. At time equals 4 seconds, the speed how fast is the particle moving at 4 seconds, and in what direction? Okay, so see how the direction was separate to how fast? That means we're dealing with speed and then its direction. So in total, it's going to be velocity, but they asked for it separately. So we're going to be dealing with speed and then direction or angle or whatever. In this case, there's no angle, it's just direction, positive or negative, left or right. Okay, so how fast is it moving at t equals 4 seconds? At 4 seconds, it is one. We're going to be moving 1 feet per second, and its direction is to the right. What is the particle's velocity at t equals 4 seconds? The velocity is going to be still the same thing, 1 feet per second. The direction being positive, which is the same thing. But let's give a different example. Let's say right here. Right here. At this point, at t equals 9 seconds, when t equals 9 seconds, the velocity, the speed at t equals 9 seconds is going to be 1 feet per second. And the direction will be to the left because it is negative. Now, the velocity is going to be both of these combined, so it's negative 1 feet per second. You get? I get. Let's go. What is the average velocity over the time 2 to 3 seconds? So from 2 to 3 seconds, let's see. Okay, so this right here is about 0.5 feet per second. So the average velocity. Okay, so what's the formula for average velocity? I want you to try to write that down. Pause the video, see if you can remember, and write it down. Okay, so here we go. The formula or average velocity, will be equal to velocity final minus plus the velocity initial divided by 2. That will be the average velocity between these 2 points. Okay, so from 2 to 3, from 2 seconds, at 2 seconds, the velocity. Okay, let's calculate the final velocity first. The final velocity is 0.5 feet per second, and it's positive, plus 0 feet per second divided by 2. So the velocity average from here to here is going to be 0.25 feet per second. When does the particle change direction? Well, okay, so we're looking for points. We're looking for points in time in which the velocity, in which the direction is changed. So when does it change direction? Well, it changes direction every time it crosses here. Let's think about it. When its velocity goes from negative to positive, you can see that it's gone from going right to going left. So that's one way. So if it's gone from positive to negative, that means it's, from negative to positive, then in that case it's going from left. From going to left to going to right. Kind of like this and kind of like this. So those are two ways in which those are the two ways in which direction can change. So it will be right when it crosses, when it changes, it goes from positive to negative, from negative to positive, or from positive to negative. So when does it go from negative to positive or positive to negative? So we got one right here. It goes from negative to positive at this point. T equals 2 seconds. And it goes from positive to negative right here at T equals 8.5 seconds. So time will be 2 seconds and 8.5 seconds. Okay, so how far does the particle move during the first second and which way? How far does the particle move during the first second? Okay, I understand the question now. Okay, so during the first second, which is going to be right here, from here to here, how far does it move? Okay, well, let's see. Let's see if we can calculate how far it moves within this time period. Okay, so for these graphs, the area under the curve, or in this case, the area under the lines, is going to be equal to the distance that is traveled. This is a topic that is covered um, in detail in calculus. I can explain why right here. So we take this point right here. Let's go ahead and draw a small graph from here to here, from 0 to 1 second. So it goes from 2 to 1 right there. Boom, 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 boom. Okay, so let's imagine this. We take this velocity right here. Let's say the velocity at this point, we're going to consider it 2. So from and this small amount of time, 2 times the small amount of time will equal some distance that is covered right here. Then we take the velocity at this point, which is slightly less than 2, let's say 1.9. 1.9 times this time, and we get the distance covered here, and so on and so forth, and we get an approximation of the distance that is traveled in this time period right here to here. If you didn't understand that, don't worry. This is a topic that this is a calculus topic. Just believe me when I tell you that the area under this curve is going to be equal to the distance that is traveled. At least if it's velocity versus time, going to be equal to whatever velocity times time is, which is going to be distance. So the area under this curve is going to be distance. Or, yeah, it's going to be distance. Well, more it's going to be more displacement because there is a direction. There's going to be more displacement in this case. Okay, so let's go ahead and let me show you how to do this. This is a bit tricky the first couple of times, but once you just learn to wing it and trust that this what I'm saying is true, then you will be then it'll get a lot easier from there. Although I do advise you try to understand this, but just for the sake of this exam, just learn how to do this for right now. Okay, so 0, -1, -2. If we can break this up into shapes that we can calculate easily, then we can calculate this entire area. So let's see. This right here. This is a square. This is a square right here. The reason I'm breaking up into a square and a triangle is because what shape is this? What kind of shape is this right here? It's a trapezoid. This is a trapezoid, or yeah, this is a trapezoid in this case. And I don't know about you, but I don't remember the formula for a trapezoid. So I'm gonna just break it down into a square and a triangle because that's what I remember. Okay, so from 0 to -1, that's the height of this square. So -1 feet per second is the height. And then the base of the square is 1 second. So 1 second, which is equal to -1 feet. So what about this place right here? So our height is going to be from here to here. The difference between -2 and -1 is -1 feet per second. That's going to be the height, and then the base is also is going to be 1 second. So -1. No, that's wrong. It's going to be -1 feet per second times 1 second. Now this is not the formula for a triangle. It's going to be 1/2 base times height for a triangle. 1/2 base times height equals the area of a triangle. So if we calculate the area of this triangle using its height and its base, we calculate that it's going to be -0.5 feet. So in total, the distance traveled is going to be -1.5 feet. And for a second, it's -1.5 feet. Okay, so there's how and which way. Okay, so perhaps they don't want the negative sign here if they're asking for which way. So the way, since the way that it's traveled is -1.5 and left is negative, then the direction that they traveled is left. Okay, so how far to the right does the particle go, and when does it arrive there? Okay, so for this question it's not applicable. Perhaps for the original graph it's applicable, but for in this case, this is an inapplicable question. What is the total distance traveled by the particle? Okay, so as I stated before, if you can break it up into parts and calculate all the areas under the graph, then we are good. We're dandy. We can calculate the well, what is the total distance traveled by the particle? Okay, so distance is going to be it's going to be additive. So it's going to be d1 plus d2 plus D3, and so on, where D1, D2, and D3, all of them are positive. Um, so if I walked from here to here to here to here, this line represents the distance I traveled. But for the displacement, my displacement is 0 relative to where I started. So there's a difference between displacement and distance. Okay, so what is the total distance traveled by the particle? I'm going to have to calculate all the areas. So height is -2 feet per second in this case, and the width at the base is going to be 2 seconds. So -2 times 2 seconds, all that times 1/2 for the area of a triangle is equal to -2 feet. But the displacement here is -2 feet, but the distance traveled here is 2 feet. Okay, so from here to here is another triangle. And this I can treat as a triangle and a square. This one I can treat as a big square. This one I can treat as a triangle. This one I can treat as a triangle, and so on. So from 2 to 4 times 1 to the base is 2 seconds. The height is 1 feet. 1 feet per second. 1/2 1 times 2 is going to be 1 feet. Okay, so right here we get the square. The base is 1 second. The height is 1 feet per second. So that's going to be 1 feet. Okay, so for this triangle, the height is going to be 2 feet per second from here to here. And its base is going to be 1 second. So 2 times 1 divided by 2. So that's the formula for the area of a triangle. That's going to be 1 feet. For this big square, we got 2 seconds and then 3. We got 2 seconds being the base and 3 feet per second being the height. 3 times 2, that's 6 feet. For this one, we got our base being 1.5 and its height being 1, 2, 3. 3 it's going to be 3 feet per second. So 1.5 times 3 divided by 2, that's going to be 0.75 times 3. That's going to be 2.25 feet. And then we have these last two triangles. This one right here it's going to have a base of 0.5 seconds and its height is 1 feet, -1 feet per second. So -1 times 0.5 divided by 2, that's going to be -0.25, 0.25 feet. And this is going to be its displacement, and its distance is going to be 0.25. From here to here, 2 seconds times its height of -1 feet per second divided by 2. So, wrong way, its height is not, okay, so its height is -1 feet per second times its base, which is 2. So -1 times 2, that's -2. Divided by 2, that's -1. So this one right here is -1 feet per second for displacement, and 1 feet, oh, no, not -1 feet per second, -1 feet, and then 1 feet would be its distance. So if we're looking for distance, we need to sum all the distances. If we're looking for total displacement, we need to sum all the displacements. Okay, so let's go ahead and calculate for both. Its distance is going to be So its distance, first part is 2 feet. Its distance covered in here is 1 feet. Its distance covered here is 1 plus 1, which is 2 feet. Its distance covered here is 6 feet. The distance covered here is 2.25. The distance covered here is 0.25. And the distance covered here is 1 feet, which is going to be equal to 2, 3, 4, 5, 11, 13, 5. Is that 25? Okay, 13.25, 13.5, 14.5. Let me just recalculate it just in case. Yep, okay, so what about its displacement? Its displacement is going to be equal to um, the sum of its displacements. So we have negative for this first one. So negative 2 is its displacement. 1 plus 1 plus 2, which is this part, plus, plus 6 plus 2.25 minus 0.25 minus 1. So its total is going to be this total is going to be 8 feet. So its displacement is 8 feet. So in other words, it traveled a little something like this. Where the line represents its distance, and the difference between here and its starting point is going to be its displacement. So this is the displacement. This line represents its distance. So let's go ahead and write that down as our answers. Interesting. Doesn't ask for its displacement. Okay, so its position after 5 seconds. So that would suggest displacement. Particle's position after 5 seconds. Let's see, right here. So, okay, so we're going to be looking for its displacement from here to here. So let's start. Displacement from 0 to 5 seconds is going to be equal to negative 2. It's going to be the sum of its displacements up to 5 seconds. Negative 2 plus 1 plus 2, which is going to be equal to just 1. 1 feet. Its displacement is just 1 foot to the right. So position is going to be 1 feet. What is the average velocity of the particle over the 5-second interval? Okay, so let's see. The formula for average velocity. I mean, yeah. We said average velocity. Yeah. The formula for average velocity, VAVG, is going to be if you have the two velocities, it's velocity final plus velocity initial divided by 2, and it's also equal to the change in displacement over the time that it took. That is going to be its average velocity as well. Okay, so see this formula only works if there is a straight line between the two velocities. You can't use this all the time. For example, if you use the average velocity between okay, just take my word for it. I'm a bit too tired to explain it right now, but okay. So its velocity average at this case, we're going to be using this formula right here, changing displacement over time, which is going to be 1 feet displacement over 5 seconds divided by 5, which is going to be equal to 0.2 feet per second. So its displacement was 1 foot, and the time it took is 5 seconds. Are your answers to 15 and 16 the same? Oh, I see the problem. Okay, so originally, the original solution, the original graph, the entire time was 5 seconds, but mine is 11. So in this case, these won't be the same. But let me change this. Not from 5 seconds, but to 11 seconds. What is the particle's position? As we calculated earlier, its displacement would be 8 feet. So these are different. Its total distance traveled versus its total displacement, which will be its position, positive 8 feet. So no, they're not the same. The position, displacement, and distance, different. What is the average speed over this 5-second interval? We have our average speed. Ooh, okay, right here. Right there, right there. Okay, so the average speed in this case, speed average is going to be equal to speed in final minus speed plus speed initial divided by 2, which is also equal to the total distance covered over time. So the total distance covered, as we calculated earlier, is going to be equal to 14.5 feet. Let me make sure. Yeah, 14.5 feet. And the time it took is going to be 11 seconds. So 14.5 divided by 11. Whatever the hell this number is. 1.32. We're going to round up to 1.32. 1.32 feet per second. Okay. So we can see that we're going to change this to 11 seconds. Okay. What is the particle's acceleration over the first second? What does your answer mean? Okay, let's see. So acceleration. What would acceleration be? I want you to write down the formula for acceleration very quickly. You got 5 seconds, 5, 4, 3. Okay, I lied. Not 5 seconds. Okay, so velocity, acceleration is going to be equal to change in velocity over time. That is going to be acceleration. So, what is the particle's acceleration over the first second? Let's see. It's change in velocity. We need the change in velocity in the first second. So from 0 to 1. So from 0 to 1 is change in velocity will be from final, which is going to be 1 feet per second, negative 1 feet per second, minus the initial, which is negative 2 feet per second. So negative plus negative, that's going to be positive. So negative 1 plus 2 is going to be positive 1 feet per second. Let's see, does this make sense? Over this time period, the velocity increased by 1 feet per second. So It went from -2 to -1. That's an increase of 1 feet per second. That does make sense. Okay, so the time that it took is 1 second. So if we plug in these values right here, 1 feet per second divided by 1 second, it's going to be 1 feet per second squared. That is going to be our acceleration. So what does this answer mean? Okay, so acceleration is the change of velocity over time. So what this means is within this time period, the change in velocity would be 1 foot per second every second. So the velocity will change by 1 foot per second every second. So every second that goes by, which at the beginning it was equal to 2 feet per second, -2 feet per second. Every second that goes by, it will go, it will, the velocity will increase by 1 feet per second. So it will go to 1 feet per second. And at this trend, if it keeps going, it will go to 0 feet per second. Okay, 1 second passes, 1 second passes, and then 1 second passes again. It will be 1 feet per second, and then again 2 feet per second. I think you get the idea. Okay, so over what time period does the particle have positive acceleration? So let's see. Okay, so I'll tell you right now, this part is quite simple if you know this trick. And the trick is going to be breaking down the acceleration formula. So the acceleration formula is equal to change in velocity over t. Let's think. So as time changes, the time will never be negative. The time will never be negative. And if we're looking for when it's always going to be positive, so in other words, when this is going to be positive, the only times in which this is unsatisfied is when change in velocity is going to be equal to 0, or change in velocity is negative, because time will always be positive. So if we have positive divided by 0 or negative, it will take either, the sign will either be 0 or negative. So we are looking for the change in velocity. We're looking for positive changes in velocity in this case. And the same goes for negative acceleration. If we're looking for negative acceleration, then we will look for a negative change in velocity. If we're looking for a constant acceleration, for an acceleration of 0, then we're looking for a change of velocity of 0. Okay, so what is this acceleration positive? So let's see, from here to here, exchange of velocity, as we've determined before, is going to be plus, okay, 0 to 2 seconds. The change in velocity is going to be 0 minus -2, so that's 0 plus 2 feet per second, so that's 2 feet per second. So this first part, we're going to have positive acceleration. We'll go from 2 to 4. 2 to 4. And remember, I'm only going parts in straight lines because it's easier to deal with. Yeah. Okay, so 1. So our final was 1, our initial was 0, so the difference will be 1 feet per second. Acceleration positive. 4 to 5. Final velocity 3 feet per second. Initial velocity 1 feet per second. The difference is 2 feet per second. Okay, so 5 through 7. Let's see, 7 seconds. The final velocity was 3. The initial velocity was at 5 seconds, so 3, and then 3. So the difference is 0 feet per second. Is this positive? No, it's not. It's neutral. It's neither negative nor positive. So the acceleration here is not positive. At this point, it's going to be neutral. I'm going to write that down. Let's note that so that we don't have to do this work again. This is positive, 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 neutral. Okay, so from 7 to 8.5. better yet, let's do 7 to 9. So from 7 seconds to 9 seconds. So 7 seconds, the 1, 2, 3. At 7 seconds, the velocity is 3. At 9 seconds, the velocity is negative 1. So negative, final minus the initial. So negative 1 minus 3 seconds, that will be negative 4 feet per second. The acceleration here is negative. So from 9 to 11 seconds, 11 seconds, the velocity, final velocity is 0. At 9 seconds, the initial velocity is negative 1. So 0 minus negative 1, that'll become 0 plus 1. So that'll be 1 feet per second, which is positive. So when is its acceleration positive? These time periods right here. So 0 to 5 seconds, it is positive. And then 9 to 11 seconds, it is also positive. So 0 to 5, and then 9 to 11. Over what time interval does it have a negative acceleration? Well, we've already gone over that. So right here is the only time that has a negative acceleration. This time period right here. Right there. That's when it has a negative acceleration. Okay, so that was 7 to 9 seconds. 7 to 9 seconds. What is the acceleration? When is the acceleration undefined on the intervals 0 to 5 seconds? So let me change it. It's not from 0 to 5, 0 to 11 seconds. When is it undefined? Okay, so I'm not exactly sure what they mean by undefined. Um, I don't believe there is a period in which the acceleration is undefined. As you can see here, the acceleration is defined throughout throughout this. So I'm going to go ahead and source this one out. State an interval of time when the particle has positive acceleration but is slowing down. Okay, so what does that mean? Particle acceleration but slowing down. Slowing down. Okay, so positive acceleration, that has to do with acceleration. Slowing down, what does that have to do? That has to do with speed. That has to do with speed. So when the speed is decreasing, but the acceleration is positive. So we just need to find an area where the acceleration is positive but the speed is decreasing. Speed decreasing meaning the magnitude of the velocity is decreasing. So here the speed is decreasing. Here it's increasing, increasing, constant, decreasing, increasing, decreasing. So let's see. Okay, so first part, it is the acceleration is positive, but the speed is decreasing. So this first part is going to be an area where the speed is decreasing, but the acceleration is positive. So 0 to 2 seconds. 0 to 2 seconds. This next part, state an interval when the acceleration is negative, but the particle is speeding up. So let's see. Negative right here, particle speeding up. Okay, so from 7 to 9, the acceleration is going to be negative throughout. Okay, so right here it is slowing down. Right here it is speeding up. So right here is the area we are interested in. It is both, its speed is both increasing. Its speed is increasing and its acceleration is negative. So right here, 8.5 to 9 seconds. What is the particle's average acceleration over the entire 11-second interval? Okay, so so remember acceleration is equal to change in velocity over time. So we just need to sum all these changes in velocity and divide it by the time in which they occur. I'm going to go ahead and do that over here again. So the sum of the total change in velocity is going to be 2 plus 1 plus 2, so that's 5, plus 0, that's still 5, minus 4, that's 1, plus 1, that's 2. So 2 feet per second is the total change in velocity. Okay, cool. Divided by the time that it takes, which is 11 seconds. So 2 divided by 11 is, I don't have the calculator. 0.18, so 0.18 is going to be the acceleration, 0.18. It's going to be positive. What is the particle's acceleration over the time interval 3 to 4? So 3 to 4, let's see. 3 to 4, the change in velocity is going to, so remember, write down the formula for acceleration, which is equal to change in velocity over time. What is this change in velocity and over how much time? It's 3 to 4. So 3 to 4, that's 1 second. Change in time is 1 second. And if change in velocity from here to here is going to be 0.5 feet per second. So 0.5 divided by 1, that's going to be 0.5 feet per second squared. Over what time interval is the particle's velocity decreasing at a rate of 5 feet per every second? Okay, this right here, I don't think, I'm not sure we'll have anything like that here. But the way you would approach this is you would calculate every time interval, you would calculate every time you would calculate the change in velocity, the acceleration of every time interval. So there'll be change in velocity over time of every time interval being here, and then you would then have the acceleration of every time interval, and from there you would be able to dictate which one had the acceleration of negative 5 feet per second squared. Now, how did I get 5 feet per second squared? Over what time interval is the particle's velocity decreasing at a rate of 5 feet per second squared every second? Remember, acceleration is the change in velocity per time. So, in this case, it'll be the change in feet per second for every second. That is acceleration right there. And it says decreasing, so we know its acceleration in this case is going to be negative. Hopefully this video helped you understand how to approach this. If you have any questions, please DM me on GroupMe, and have a wonderful day.